use and construction method. I believe that the presence of international experts with abundant experience in the design and construction of modern bridge in all over the world, like our four speakers today, Mr. John Anderson, Dr. Andrea Mortini, Mr. Kuo Bin Lee, and Mr. Ahmadi, will be very beneficial to us. Through this webinar, I do hope that Indonesian engineers will be encouraged and motivated to deepen their knowledge in all aspects related with non-conventional bridge and be ready to take a part actively in the development of modern bridge in the future. In closing my speech, I hope this webinar will go on smoothly. The discussions be conducted positively and fruitfully, and finally will bring in benefits to all of us, civil engineers and Indonesia's construction sector. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Yeah, thank you for the opening remarks, Pak Insinyur Bambang, our chairman. And let's move to the next agenda, which is basically the webinar session. Before I pass the leadership of the event to Insinyur Wendy Aritona, IPU. Firstly, I would like to introduce, we have Pak Mulia, Pak Insinyur Mulia dari Kepulauan Riau sebagai Ketua PII Kepri, sebagai organizer kita, dan Pak Insinyur Prastiwo juga dari PII Cabang Batam. Terima kasih Pak Mulia, Pak Prastiwo sudah mengorganize kegiatan buat PII BK Sipil ya. Kira-kira seperti itu Pak.
Yeah, thank you. You're welcome, Mr. Habibi. Thank you.
Oke. Oke, Pak Wendy, silakan Pak. Time is yours, Pak. Yeah.
Okay. Thank you, Pak Habibi. Can you hear me clearly?
Yes, we can hear you clearly, Pak.
Okay. Very good afternoon, para participant and distinguished speakers. Thank you, Pak Bambang Guritno, for the opening remarks. In this webinar today, we have four speakers, as mentioned by Mr. Habibi. We have Mr. John Anderson, from General Manager of SMAC International Africa Division. He will talk about Sydney Metro Cable Stay Bridge concerning the precast segmental concrete and cable stay construction technology. Our second speaker will be Dr. Andrea Mordini, from Bridge Engineer of BGNE. He will talk about the world modern bridges. And the third speaker will be Mr. Guo Binli from China. He's the chief expert for China Communication Construction Technology Infrastructure Technology Group. He will talk about technical innovation and performance improvement of long-span bridges. And our last speaker will be our friend, Mr. Ahmadi Tricahyono, Head of Engineering Division of PT Wijaya Karya, who will talk about the construction of new bridges in Indonesia. Mr. John Anderson, you are with us? John?
Yes, no, I'm
Okay.
ready. Thank you. Yeah.
Okay. Without further ado, I would like to give the floor to Mr. John Anderson. John, you will have a maximum 30 minutes because with four speakers, altogether will total 2 hours. And the last 1 hour, we will dedicate it for the question and answer. John,
Okay.
the floor is yours.
Thank you. Can I just ask, I'm going to share my screen to show my presentation. Yes?
Yes, sure.
Yes. Okay, that's it. Okay, so just give me an opportunity to do that.
By the way, before John starts, I would like to remind our colleague participant that you could address your question or you ask for clarification via the chat facility. You can write down in English and also in Indonesia. Just feel free.
Okay.
Sorry, John. Thank you.
Before I start, can I just ask, can everyone see my presentation? It should say Sydney Metro Cable Stayed Bridge.
Yeah.
Yes. That's good.
Okay. Okay, not to take up too much of my time, but I'd just like to thank you for the invitation and the opportunity, and to greet everyone. Today's presentation I'm giving is about the Sydney Metro Cable Stayed Bridge. As the introduction mentioned, I sit in Cape Town, but this is a bridge that we designed in Sydney. This is the bridge. It's essentially a extradosed rail bridge. It carries 2 lines of metro. It was built using precast segmental construction techniques, and it's got a main span of 131 meters that crosses Windsor Road in northwest Sydney, and its pylon sits centrally on top of the superstructure, and then the superstructure sits on bearings on top of the piers. The bridge is quite a busy urban environment, and there wasn't a lot of space, so that was the main reason why we chose to have the pier sitting centrally, and perhaps not having, you know, your more typical type of A-frame or H-frame or even independent towers on the sides of the deck. What's perhaps most unusual about this bridge is the way it was built. It was built using standard precast segmental construction technology, using an overhead gantry, and it was first built as a girder, a continuous girder, on the permanent piers and a number of temporary piers. Thereafter, the towers were installed, the fin was installed, and the cables were installed, and the bridge was essentially converted into a cable stayed structure, and the temporary supports removed. And that fact was instrumental in how the bridge was designed and how the bridge design developed. The cable stayed bridge is actually part of a much larger project. The clients in Sydney have developed, have extended the metro from the centre of Sydney out to the northwest, and the project at one stage was the largest civil engineering job in Australia, and it included tunnels and this viaduct, which is about 4.5 kilometers long, that leads up to the cable stayed bridge itself. The approach viaduct to the cable stayed bridge is your normal simply supported spans and a number of continuous spans. They're 2.5 meter deep precast segments, and they're built with an overhead gantry. And the contractor actually used a fairly massive gantry that could allow them to construct the 3-span continuous system as well. But the requirement for a long span crossing was actually an alternative in the design and build tender. Contractors had to price both the conventional structural system with the simply supported spans, and then also develop a long span option. And the contractor that we worked for, one of their key strategic objectives was to build the cable stayed bridge using the same overhead gantry that was going to be used to build the simply supported span. And in the end, that decision was the winning factor in the tender. So today I'm just going to go through some of the design challenges with the permanent works, and then also just talk a little bit about the construction sequence and how that actually informed design itself. So general advice is perhaps stay away from cable-stayed rail bridges and stay away from curved cable-stayed bridges. This bridge combined both. There was no real alternative given the alignment of the rail was set. But with any rail bridge, you need a stiff deck, obviously, to limit deflection, to limit the rail stresses. And that could be a challenge with a cable-stayed structure, which generally has flexible deck. So the structural system is an extradose bridge with a stiff deck, and that stiff deck helps you to limit the deflection of the bridge itself, and as I say, limit the rail stresses and the tolerances on the rolling stock. Part of the performance objectives or the design requirements for the bridge was that the deflections actually had to be limited under rail loading to less than span of a 950, which is fairly tight for any suspended cable-stayed bridge. The other big constraint we faced was from the urban designers, and the need to limit the deck depth to 3.5 meters. Given it's a busy urban area, they wanted to limit the visual impact of the bridge itself. But this constraint proved very difficult for the designers, mainly because of the magnitude of the rail load and the magnitude of the superimposed dead loads that you often get with rail structures. So in a conventional cable-stayed bridge, it's the cable stays themselves that often provide the stiffness in the structure. Most of the load finds its way to the cables and to the pylon. You have local bending effects in the deck. So obviously that structural system is not suitable for a rail structure. So with the rail structure, you have a much stiffer deck, but when you combine a stiff deck with cables, then the sharing of the load between the stiff deck and the cables themselves becomes a little bit more complex. Generally what happens is with these stiffer decks that you can build the bridge in such a way that the cables take the dead load of the deck, but when you apply live load to the structural system, the girder is far stiffer and therefore attracts the majority of the live load effects. And typical span to depth ratio on a constant depth extradose bridge would be span over 35. So for the Northwest Rail Bridge, that would be a deck depth of about 3.7 meters. So although 3.5 is relatively close, I think these limits are generally developed for road highway structures. And when you have rail structures, the live loading component is fairly onerous. And as I mentioned, the superimposed dead load was fairly onerous. Now, extradose bridges, where you have constraints on the deck depth, one option is to haunch the deck, and that can be very effective in having a local haunching at the pier support. But again, in this instance, our urban designers would not allow us to do that. So we had to retain the constant deck depth to essentially tie in with the main viaduct. So this fact presented quite a number of challenges. And together with the curved horizontal alignment, had us fighting between the capacity of the deck and the capacity of the pylon. Generally, cable-stayed bridges are straight. You have primarily the load effects are longitudinal, but when you have a curved cable-stayed bridge, you introduce transverse load effects into the structural system. And that manifests itself in transverse bending in the pylon often, transverse bending in the deck, and transverse reactions in the bearing supports. So the cables followed the alignment of the bridge. They're therefore not in a single plane. They're splaying, and this fact introduces lateral horizontal reactions at the anchorages in the pylon, which then introduces a permanent bending, transverse bending in the pylon. So this is far from ideal to have this permanent effect within the pylon, and it becomes critical to limit the amount of transverse bending that you generate in that pylon. So, through the tender design process, we found that we were struggling to get the deck section to have sufficient capacity at ULS, and then also prevent tensile stresses developing in the precast segments at SLS. In a rail structure, you're required to maintain a minimum of 1 MPa across all joints. And then the other challenge that we had was limiting the transverse moments in the pylon, and then limiting the transverse deflection of the pylon, because as it deflected, it introduced second order effects into that system and magnified those transverse moments that were being applied to the pylon. So as I mentioned, with one of the sort of characteristics of extradose bridge is that you can often use a higher maximum force in the cables. I think it's 60% of the guaranteed ultimate tensile strength you can use in an extradose bridge, where in a cable stay bridge, you're only allowed to use 45% of the ultimate tensile strength of the cables. And the reason for this is because in an extradose bridge, the stress range in the cable is far lower. And the reason the stress range is far lower is because much of the live load effects are carried by the much stiffer deck section. Now, obviously, the stiff deck helps limit deflections, but the downside of it is it's also attracting load, and this became a real problem in terms of finding sufficient capacity within the deck section itself. So we had to find solutions of attracting more load to the cables and away from the deck section to actually get the structure to work. And this required a number of unconventional approaches, and one of them was to actually just increase the stiffness of the cable stays themselves, which essentially means just using larger cables. So by using larger cables, we attracted load away from the deck and towards the pylon. But that was a double-edged sword in some respects, because the more load we attract towards the pylon, the greater the transverse effects in that pylon. There was a very definite limit about the amount of transverse load effects that we could take in the pylon. Obviously, another way to get more load into the cable stay system is to increase the height of the pylon. But again, that was counterproductive, because the higher the pylon, the larger the transverse bending moments. So we were stuck with this balance between attracting load to the pylon, but not increasing the height of the pylon itself. So first option that we investigated was increasing the capacity of the box section. We weren't allowed to increase the height of the box section itself. So we came up with this idea of introducing a central web with a concrete fin that projected above the box section to give it some additional stiffness. But this was a design and build job, and the contractor was not keen on any solution that interfered with this precast segmental production cycle. And this central web was obviously something that would do that. So in the end, we had to develop a solution where we had the fin projecting above the deck level, but we had to get rid of the central web. So the question then becomes, well, is that fin going to be effective within the section? Is it actually going to meaningfully increase the stiffness of the section? So the way we investigated that was a brick model of the deck section, and what we found was that the fin was effective. It did meaningfully increase the stiffness of the deck section, and the reason for that is when you have precast segmental construction, you're required to have compression across the joints. So the section itself was always in compression, even under the live load effects. So this meant that there were minimal shear lag effects within the deck section, and that this isolated fin in the middle of the deck was actually fully effective and meaningfully increased the stiffness of this. So this was a nice benefit of the precast segmental construction design process. Another idea that we had was to put the anchorage, the deck anchorage, the cable anchorage in the deck eccentric to the center line of the deck section. So we moved the anchorage to 500 mil to the outside of the curve. And what this did was it reduced the overall resultant horizontal effects that were applied to the pylon, and therefore reduced the bending moments of the pylon. And this was actually one of the most important deviations from perhaps a standard layout that was a direct response to the fact that we had a curved deck. And the other big benefit of that was that it reduced the torsion in the deck. So hopefully I can explain this, but on this slide, you see I've written the outside of the curve, and you can see that the anchorage is placed towards the outside of the curve. So if you imagine something on a curve, the outside edge wants to deflect further than the inside edge. So the fact that you have this eccentric cable connection is essentially pulling that outside edge up, and it introduces a relieving effect. That green arrow is the relieving torsion that's applied to resist or counteract the dead load torsion. So this placing the deck anchorage eccentric to the center of the line of the deck section had a number of benefits that we relied upon. So just to talk a little bit about the pylon itself. The pylon was fabricated as a structural steel section, and this was done really for production reasons. As we were building the girder, we could build the pylon. It's a 28-meter high section, and it was transported and erected on two-sided and erected with this crane. What we did is we filled the bottom half of the pylon with concrete, and created a composite section. And the big benefit of that composite section was its stiffness. A composite steel section was far stiffer than a pure concrete section. And that stiffness helped limit the deflection, the transverse deflection of the pylon, and then helped limit the second order effects. So it had a big benefit. The fact that the transverse bending moments were permanent effects meant that there would be some concern about just using a standard concrete section and the creep of that concrete over time. Those concerns were allayed by using essentially a steel section, and then the stiffness of that steel section was augmented by filling the bottom half of that pylon with concrete. So the bottom half of the pylon had basically was bolted down onto the steel section. We had access in there. The reinforcement from the concrete fin ran straight through the bottom of the pylon, and then it was filled with concrete, as I say, to create that integral connection between the pylon and the deck. I think the only negative of this approach was access to the cable anchorages, and you can see in that bottom left-hand image, we had to create access from above, and an access hash to get in from above, and that wasn't ideal. Generally, you'd want access from deck level, but in this case, the challenges with the structural system was such that we had to live with that compromise. So maybe just to go back to what I mentioned about changing the cable stiffness and how that affected the behavior of this extra nose bridge. What we did is during the design stage, we did a sort of optimization study where we looked at the impact that increasing the cable area had. So the largest cable stay you can get is a 185 strand cable, which is a fairly massive unit. So the first option was just to use the largest cable that we could. Then we looked at second option, reducing those cables down to a 169 strand, just on the outer two cables, which take most of the load, and then reducing the size of the remaining cables that fan towards the pylon. And then we looked at two other options, 3 and 4, where again we just progressively reduced the size of the cables themselves, the number of strands, the area. So this slide is a little confusing. We looked at the sagging moments in the main span, which is essentially the blue line at the top for option 1, 2, 3, and 4, and then the maximum sagging moments in the back spans, which are those other 2 lines. But essentially, what we found was changing the area of the cable did not change the maximum sagging moment in the deck section. This wasn't the case for the maximum hogging moment at the pier. We found that that as you went from option 1 to option 4 and 5, the bending moment definitely increased, the hogging moment. Sorry, that's a negative value. So the bending moment increases as you go from top to bottom. And the bottom 2 lines are the hogging moment on the main span, either side of each pier. And what you can see is that, after reducing the area, you get to a point and then it has little effect, but at some stage, increasing the area does have a very big benefit to reducing the bending moment in the deck section. So I'm now just quickly going to go on and just talk a little about the construction and erection engineering, because that informs so much of the design that we, the way we built it was really drove the whole detailed design. And just to sort of familiarize yourself, because I'm going to show you a number of slides in terms of how we built it. I'm just going to, we've got the main piers are Pier 112 and Pier 113. And then we've got the pier adjacent to the main viaduct, 111. And then those TP1 to TP5 are the temporary the temporary piers that we introduced while we were building it. And these temporary piers were instrumental in allowing us to use the overhead gantry. Obviously the gantry's got to jump from one hard spot to the other. So by using these temporary piers, we were able to build the continuous girder with the precast segments first, and then later converted into the cable stay bridge. And you can see the sort of Windsor Road clearance envelope there. But during the construction process, the road remained open. We lifted segments at night and only closed the road for a limited period between 12 and 4 o'clock in the morning. So generally, when you use overhead gantry, you start at one end and you progressively construct to the other end. I'm just going to show you quickly the kinematics. So there you go, Pier 111 at the end of the main viaduct. The gantry jumps forward onto those hard supports. You have infill segments on either side of the TP5, and then the gantry jumps creates a small cantilever section at Pier 112, and the length of that cantilever is set by the length of the temporary span. So then you have your infill sections, and that section progresses forward. Again, TP3, you have a small cantilever that's set by the length of the span between TP3 and TP4, the infill segments, etc. And the gantry can progress from one end to the other. Now, we did that, we tried that, but what happened was that the pre-stress that you need for the construction stage proved detrimental in the final stage. So the fact that we were building these small cantilevers, putting the pre-stressing in, and then subsequently converting the bridge into a cable stayed bridge meant that we had undesirable peaks in the pre-stressing. We had higher compressive stress and lower, and we had tension in the deck section. So there was no way that we could start at one end and go to the other. We had to find a different construction method that mimicked the behavior of the permanent works rather than the temporary state, because there was no way that we could detension. Sorry, how much time?
3 minutes to go, John.
3 minutes. Okay, so I'm going to run through this very quickly. So in the end, what we did was we started at Pier 113 and we built a very long cantilever to start with, and we got the pre-stressing in for that. Then we finished the back spans. We drove the gantry back across the road. We then built a very long cantilever at Pier 112, and finished the back spans, and then came across and finished the main bridge. Now, the big benefit of that, was the pre-stressing that we needed for these long cantilevers essentially was effective in the permanent state when we converted the bridge into a cable stayed bridge. Okay, so just a little bit of insight into the construction engineering, very complex, over 110 construction stages. During that construction, the bearings, we had to have multi-purpose bearings. They had to be fixed, they had to slide, so they had to change their function. So what we did is we had jacks sitting on sliding pads, and then we created these plinths. And we had plates essentially bolted to the underside of the deck, and we could clamp those plates around this plinth. So we could have fully fixed, we could have, fixed longitudinally or fixed transversely. So we could change the functionality of those temporary bearings relatively quickly. Just going to skip that. So the fin itself was quite a complex element. Because it's quite a narrow element, it attracted peak tensile and compressive stresses. So it was packed with reinforcement, and we had to use self-compacting concrete. But one thing that we had to do was, because it was reinforced and the rest of the deck was precast and pre-stressed, we had quite a big stress differential in the composite section. So we had to jack the deck upwards before we cast the deck to improve that stress profile. And then after we cast the fin, we jacked the deck up again so that we got relieving effects in the fin. And then just one important point is, with the extra nose bridge, you cannot change the geometry by stressing the cables. The only way you can do it is by jacking the deck up and shortening the cables. So this jacking operation also had big benefits in that it was one way that we could increase the reaction at the temporary support. And by doing so, we were able to get more load into the cable. That became a big part of our construction methodology. So in the end, it looks a very simple bridge, but its construction methodology made it was actually very complex, and but you know, as I say, we're very proud of the way the bridge looks, and its complexity is sort of hidden within it. So that's everything. Thank you very much.
Thank you very much, John. It's really interesting. Yes, as you mentioned, it looks like just not so much technology sophisticated in terms of in terms of the span, because it's not too long, but in terms of the complexity, because this is really I don't know what to call it, the cable stay hybrid, because this is the hybrid between the cable stay and the precast concrete put together. Very interesting. So, John, we will hold all the question later on after all the speaker finish with the presentation. Ibu Bapak sekalian, memang yang dipresentasikan oleh Pak John ini secara kabel sales sebetulnya nggak terlalu secara panjang ya, nggak terlalu signifikan sebetulnya, biasa-biasa aja, mungkin sekitar 300-an kita juga punya. Tetapi karena bentuknya yang melengkung ya, sambil itu melengkung tidak lurus, itu alignmentnya melengkung karena untuk mengakomodir jalan kereta api yang nggak bisa terlalu itu, maka menjadi menarik karena kemudian dikombinasikan antara teknologi beton precast dan teknologi cable stay. Optimasi di antara dua itu yang mungkin menarik bagi bapak-bapak untuk nanti kita diskusikan dengan Pak John Anderson. So with that, we can continue with the next speaker, Dr. Andrea Morini. Andrea, are you there?
Yes, can you hear me?
Okay. We
yes.
can hear you very clear.
Thank you. Thank you.
So
I will,
your time is yours. You have 30 minutes, please.
Sure. Thank you. I will first of all try to share my screen. Could you confirm that my screen is visible?
Yeah, it's there.
Okay.
Just perhaps you put full screen if you like.
Okay. All right. Okay, thank you. First of all, I want to thank Mr. Chairman, Mr. Bang Bang, and the moderators, Mr. Aritnang and Bibi. You will forgive my pronunciation. And a special thanks also to the Institution of Engineers in Indonesia for giving me the chance to present some of my experience in bridge engineering and construction. This is me. I'm originally Italian, and I was lucky enough to have some experience in interesting projects in a number of countries. And I will take you today on a trip, and I will show you 3 different bridges, each of them with different challenges. I'm currently based in Singapore, where I lead the bridge team for BG&E, International Consulting Engineers. Couple of words about the company. BG&E is an Australian founded company, and nowadays we have accumulated more than 50 years of experience, and we count more than 700 employees. Of these, about 150 are bridge engineers. And I said we are originally an Australian company, but we have expanded our national footprint with 11 international offices that you see here on this map from London, Middle East, Singapore, and then of course our stronghold in Australia, all the way to New Zealand. And we are also active on the Indonesian market with currently with some projects, and we went through the local registration process. Currently, the bridge team in Singapore is busy, among others, with two main projects. One is the North-South Corridor, which is a viaduct structure cutting the island in the north-south direction. And the other one is an MRT project, the Jurong Regional Line. After this short introduction, I go into the presentation and I start taking you to the Netherlands. And we will have a look to this bridge, and you can tell immediately that the main characteristic, the main property of this bridge is to be a movable bridge. Let's try to have a closer look. The Botter Bridge is one of the largest movable bridge in the world. We are talking of two steel decks with a span of 92 meters for a structural steel weight of 3,600 tons each. Each deck can go up in the air about 45 meters. And you see here that we are talking of fully balanced lifting system. Fully balanced means that when the deck goes up, like in the first deck here that you see, I hope you can see my pointer, or I try maybe.
Yes, we can see
yes. Okay, now it's. I hope it's clear. When the deck goes up in the air, the counterweight, the two counterweights that are positioned on the sides go down. When on the other side, the deck is down on the bearings, the counterweights are up. Deck and counterweights are connected by a system of cables that you see here, going up to the top of the tower and coming back inside the tower. I also wanted to highlight some data about the concrete casting. I put down the cubic meters for each of the elements. I want to underline the underwater concrete that has been cast to realize the underwater piers here for a total amount of 44,000 cubic meters, which is quite a relevant challenge from the logistic point of view, and I believe one of the largest cast worldwide. Closer look to the cross section. We have three main trusses carrying the weight longitudinally, and we have the use of orthotropic deck. Usually still orthotropic deck. Usually you would like to avoid the use of orthotropic deck for the problems related to fatigue, also because the Dutch national annex is very strict about fatigue. However, in this case, it was an obvious choice because we needed to limit the weight of the deck. You see the other big challenge is that both the bridge is carrying both highway lanes and railway lines. And this, of course, creates an additional challenge for the different requirements connected to highway and the railway. Some other challenges that I can mention. The bridge was built with a mix of design and built with a mix of national codes and the Eurocodes. And it was necessary to integrate different requirements from different stakeholders, the owner of the waterway, the owner of the highway, the owner of the railway. And we had also very strict requirements regarding the reliability, with high non-performance penalties that you see here in the range of 100,000 euros per 50 minutes per lane. So if you close a lane for 50 minutes, you have to pay $100,000, 100,000 euros, and a quite short opening and closing time of 90 seconds, which may look long, but when you have to move 5,000 tons of permanent weight up in the air, I'm sure that the mechanics behind it, the M&E component is quite challenging. And then, of course, from the construction point of view, the bridge has been built when the infrastructure near it were still in operation. Of course, the waterway, and then the old bridge. You can see behind the white bridge, there is a blue bridge, which is the old bridge, and it was still in operation. And on the other side of the bridge, there was a nearby tunnel. All those structures have been monitored during construction. The deck itself has been produced in segments in Hanover, in Germany, by Eiffel. And to limit the weight of and the thickness of some of the sections, the steel 460 has been used, which presented some additional challenges from the production point of view. You have more strict requirements for the welding operation of steel S460. After the production, the segments have been transported by track to Rotterdam, and they've been assembled together in an assembly yard a few kilometers away from the site. This is an overview of the assembly yard. The decks are almost completed. And you can see the tents that are used to perform the on-site welding. And I want to underline that this yard was had a direct access to the water, as you can see here. And the importance of this, I will try to show you now in a video. Let me try to get out. Okay, I have the video ready here. Yeah. Okay, this is the deck that has been completed and assembled. And as a first step, it has been jacked up, and a multi-wheeler has been slid under it. And then slowly, the deck has started moving towards the water where a barge was located. See, the operation were very slow because the barge has, of course, to compensate the load coming in from the deck. This is, of course, a time lapse. Now deck is fully on the barge, and the barge can move towards the end destination, which is, as I said, just a few kilometers away. Before being installed, there is another challenge. The deck has to pass through the old bridge, and the old bridge has a smaller span than the previous one. So now the old bridge is open and the deck is moved past through. It's a quite complicated operation if you think that the clearance on both sides is less than 500 millimeters. And even a part of the bridge actually will be, an edge of the bridge is missing, you will see, and it has been installed afterwards. Now the deck is fully on the other side, and it has been rotated, and now it is in position, ready to be installed in its final position. Another quite watchmaking operation to fit half of a football field between the piers. You see that here an edge of the deck is missing. Those are the latches to connect to the cables, because there was a very limited time window to perform this operation, and then immediately the deck has to go up in the air to free the waterway. And yeah, this is the completion of the operations. Let me go back to my presentation. After the installation, there was a testing period. You see here, both the decks are up in the air with some ballast, because the full permanent load must be already on the deck because of the full balance system. And this is the completed bridge as it is today. After this movable bridge, we fly all the way to Australia. We talk of the Nepean Bridge. The Nepean Bridge is a shared path, cyclist plus pedestrian bridge. Is a part of the Great Eastern Highway project, and in this case, BHNE was the detailed designer for the authority. And to overcome some constraints on the side, we have developed a quite interesting concept for the launching. The bridge has a clear span of 200 meters, and it is a truss bridge. And we know that trusses work well when they are supported in their nodes. But this is exactly the opposite what happens when you launch a bridge, because when you launch a bridge, the deck is supported in each and every point of the deck in different moment as you slide the bridge. So to avoid this unfavorable load support configuration, BHNE has developed a system whereby the deck is here, is supported at the node, and instead of sliding the deck with respect to the support will be fixedly connected to the deck at the same point, and the support itself will slide on the tower. It's not by chance that the length of the tower is exactly the distance between two nodes, and also the distance between the towers in the river is actually exactly the distance between two nodes. Let's have a closer look to this system. We have a look here. This is the first part, the first segment that has been launched. And you see the system works like this. Here we have jacks to engage this bearing, and this system of bearing and jacks will be fixedly connected to this node. And then the bearings are connected to this crossbeam, and the crossbeam will slide on this rail. Same view from another perspective of the same system. This is the end of the launch. We are at the last segment, but this mechanics is repeated all along the bridge for the entire 200 meters. After visiting Australia, we fly back in the Middle East, and we land in Bahrain. We are still talking of a launch bridge. This time is a concrete bridge. And yes, this is an overview of the site. We have the bridge is taking off on this side, and then we can see already the piers already built. This is the alignment, and it will land down on this other side where the other abutment is located. We are talking of 550 meters of total length for 14 meters of span. 14 total number of span. BGNE in this case has performed the detailed design of the bridge and the casting yard, and including the geometry segmentation and the construction engineering during launching. I want here to focus for a moment the attention on the segmentation part, because the geometry of the bridge is actually very complicated, because we have a double curvature. Of course, we have a curvature in plan, as you can see on the left side, but we have also another curvature in elevation, because the flyover starts here with a low point, it goes all the way up, and then it goes down. So this is the geometry in the 3D view of the alignment, and this has been translated into the geometry of the deck with multiple cross-section taken along the alignment. If we look more into the cross-section, we have to notice a couple of things. The first is that the client dictated a constant crossfall on the ramp. And this means that this has to be taken into account already in the casting yard. And to be able to obtain the final right geometry, our drafting team has had to prepare one section for each meter to provide the longitudinal variation of the crossfall. The other one thing that the client dictated was the use of the double cell. You can see that the width of the deck is quite conventional. The width of the cantilever is not extreme. We have actually recommended the use of a single cell. The client actually wanted to use a double cell. And this was partly justified by the very strict requirement that we had to apply, because for this contrast specifically was adopted a crack width of 0.1 millimeters, which is quite strict. Now, more on the construction side, this is an overview of the casting bed before the casting of the first segment. You see that the nose is still located near the first segment, still in the casting yard, and the casting bed was divided into 3 stages. The first, the assembly of the rebar cage, then the second was the casting of the W, so the bottom slab and the webs. And the third stage was the casting of the top slab. The segment length was about 20 meters, which is about 50% of the main span. And total number of segments was 226. And after an initial learning curve, the cycle time was actually 1 week. I mentioned that the ramp was the total length was 550 meters, so you need some expansion joints in the middle, and to allow for the bridge to be launched, the expansion joint were cast together with a bond breaker and tension bars. And then once the deck is in its final position, then by using jacks, the expansion joint have been opened, and the three big units reached the final position, and then later the expansion joint have been installed. We have a view now to the system that has been used. The specialized subcontractor has selected a pooling system that basically works as per this sketch. We have a system of jacks which is connected to the first abutment with some steel structure and tension bars. And the jacks are connected longitudinally to tendons that are fixed here, you see on the other side, to a sticking beam. And this pulling stick is actually passing through the deck, both the bottom and top slab. And what happens is that the jack will pull on this side, and the idea is that through these tendons, the pulling force is transferred to the pulling sticks and then toward the deck. Of course, you have a relevant force introduced into the abutment, and as you see depicted here, also a relevant push and pull action inside the top and bottom slab of the bridge. Here you see some photos of the side. The nose was realized also. Curve was in steel, of course, and it had to be built with a curve shape to follow the alignment. Another close view of the side with the engagement of the nose with a pier. And since we have a launching system, there is something moving. So let's try to have a look again at the video. All right, here is an overview of the site. The launching operation started usually in the evening and were performed during night. This, of course, is not the first segment. You see that the irrelevant part has been launched already. This is a close view to the check-in system. And you see that the launching is performed above live traffic. Here are the last measurements and checks before the beginning of the operation. Here is a closer view and preparation of the pulling system. And finally, we start. You see that the jacks are pulling and the bridge is moving on top. Once the stroke is completed, you see that the tendons will become sagging. This is an overview of the pulling stick coming down from the top of the deck. And you see the bridge moving. This is a temporary bearing, the temporary support in the casting yard. And here, if you focus on the bridge, is a time lapse. So you will see, yeah, here you are. You see the bridge moving step by step. Of course, it's not a continuous movement, but is each time the bridge will move according to the maximum stroke of the jacks. Here some other time lapse. You see the bridge is still advancing. Here you have another step, and the operation went on and on for several hours. You see now it's already early morning hours, and the operations are quite completed. And here you are now, it's a full day, and this is the final configuration of the bridge for this for the casting of this specific segment. All right, I think I'm through with my presentation, yes. So I want to thank you for the attention. And of course, I will be happy to answer any question in the following phase. Thank you.
Thank you, Andrea. Thank you very much for the very enlightened presentation. We'll continue with our third speaker, Mr. Guo Bin Li. Mr. Guo from China. Are you there? Yes, Mr. Bin Li. Hello. Mr. Guo Bin Li.
Yes, I'm here.
Oh, okay. Okay, you can start your presentation. Again, you have
OK，是这个吧？谢谢。OK, good afternoon, everyone. Right, to webinar, I have the chance to share my understanding and opinion.
Mr. Govin Lee.
About
And also see your presentation.
I'm very
Mr. Govin Lee, are you still mute?
Now it's okay?
Now we can hear you.
Okay.
But
now
we don't have your presentation yet.
Just a moment. We'll share the screen.
Arctic Bridge in Greece is the existing oldest bridge. It has a history of about 3,000 years. And Zhaozhou Bridge is the oldest bridge in China now. Lujing Bridge in China is the first 100 scale bridge in the world. And Washington Bridge, USA, is the first 1,000 meter scale bridge in the world, the first 200,000 meter scale bridge in the world. We all know that there are four basic bridge forms. Bridge, 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 and the Cape State Bridge. We will found that the span lines has most reached the ultimate limit.
Pak Habibie, are you there, Pak Habibie?
Yes, Pak Wendy.
Ini Bapak kedengar suaranya Pak Gobind enggak?
Nggak ada juga kedengaran, Pak. Sepertinya dia menghilang. Oh, ini baru mau masuk lagi. Ya, udah masuk lagi.
Sorry.
Gobind Lee, are you still there?
Ini Pak Gobind Lee yang CWB 1 itu ya? Pak Habibie. Panitianya, Pak Habibie.
Sepertinya dia ada kendala ini, Pak, kendala jaringan. Mungkin kita bisa lanjut aja mungkin ke pembicara keempat, Pak Wendy.
Oke.
Ya.
Mr. Gobind Lee, you still mute. Because it looks as if that we have a connection problem with you because we cannot hear you and it's interrupted many times. So I would like to suggest that we will continue with the more speakers while you try to fix your connection problem.
Oh, he's already here.
Oh, you already here? Okay.
Yeah, the slides already shown.
Okay. Sorry, some problem about my net.
Yeah, please continue, Pak.
Okay, now let's continue. This table is the top 10 long span concrete span bridges, and there are 4. There are 5 bridges in China. The second is about arch bridges. Arch bridges have a history with over 3,000 years. This is the evolution of the longest span of arch bridges. It can be found that the longest span only increased 14 meters from 1931 to 1977, but it increased rapidly in recent years. This is the top 10 long span arch bridges. There are 7 bridges in China. The longest span is 575 meters. China has had a long history of arch bridge buildings, and now still owns a number of world records of the longest span of arch bridges. This is the Stone Arch Bridge. Its max span length is 146 meters. Concrete arch bridges, the span length is 445 meters. The concrete filled steel tube arch bridge, Pingnan Third Bridge, the span length is 575 meters. It's also the longest span arch bridges in the world now. This is the steel box arch bridge, 550 meters. And this is a steel truss arch bridge, 552 meters. The third one is about serpentine bridge. Serpentine bridge is an ancient bridge form, but the long span serpentine bridges were developed with the increase of material performances of steel after the late 19th century. This is the evolution of span lengths of serpentine bridges. It can be found that the longest span reached over 1,000 in 1931 and increased gradually since then. And the table is the top 10 long span serpentine There are 5 bridges in China now, and the longest, the left picture is the Center Street Bridge in Indonesia. And the Shuzhuyang SS Bridge is heritage. Cable Stay Bridge is a structure prime component, towers, girder, and cables. This is the evolution of span lengths of cable stay bridges. From that, the longest continually and has potential for longer span. This is the top 10 long span state bridges. There are 6 bridges in China and 4 meters. Rocky Bridge in Russia. Tongtaiyang River Bridge now is being constructed. Its max span length will be 1,176 meters. It will be the longest span after its completion. Part 2 is challenges and the engineering approaches for longer spans. First, talk about beam bridges. For beam bridges, the maximum negative bending moment will control the longer span. This is Humen Bridge. Its max span length is 217 meters. The negative bending moment is 4,000 milliNewton meter. If the span length to be longer, the bending moment will be higher, and it's very difficult for the second size and pre-stretching tendons. So we introduce the open spandrel girder. The Panjiang River Bridge, the main span length is 290 meters. It's like a girder and arch combination structure. And we can also adopt concrete and steel hybrid girder. Shibanhuo Bridge in China, the old bridge is a PC continuous rigid frame bridge. And besides the old bridge, a new bridge is built, and the maximum length is 330 meters of negative bending moment. The 108 meters girder is replaced with steel girder, and the negative bending moment at the main piers is close to homing bridge. Another approach is adopting heterodose Cape State bridge. Heterodose Cape State bridge is a hybrid between beam bridge and the ordinary Cape State bridge. With the help of steel cables, it can reach longer span with smaller girder depths. This is the comparison of girder depths between PC beam bridge and the heterodose Cape State bridge concrete bridge. It can be found that the girder depths can be reduced a lot. The picture is Wuzhou Fujiankou Bridge. It's an heterodose Cape State bridge with pre-stressed concrete girder. Its main span is 2,270 meters. It's the longest of this structure type in Asia. The second bridge is arch bridges. One challenge here is the buckling stability of arch labor for longer span. With the increase of span length, calculation length, and compressive stress of arch labors shows the increase of span length. Especially for both general and local stability is not good. So one approach is use the concrete filled steel tube labor arch bridge. Concrete filled steel tube is the composite structure of external steel tube and the concrete filled inside. External steel tube has better local stability resistance due to the infused concrete, and the concrete has better strength and ductility. Pingnan Third Bridge in Guangxi, China is a CFST rib arch bridge. It was built last year. Its main span length is 575 meters, the longest span of arch bridges in the world now. Its construction includes first cantilever installed steel tube rib with the help of temporary steel cables to form the steel tube arch. Then fill concrete into the steel tubes in batches to form the concrete-filled steel tube composite arch. Then construct columns, suspenders, decks supported by arch rib to form the concrete-filled steel tube arch bridge. Another approach is concrete-filled steel tube stiffened concrete rich arch bridges. CFST stiffened concrete was first used in China as the stiff skeleton to build concrete arch bridge. The picture is the Pan River Bridge in Guizhou, China. It was built in 2015. Its mass span length is 445 meters. Construction of the steel stiff skeleton. They fill concrete in the tubers to form concrete-filled steel tuber stiff skeleton. Then install formwork supported by CFIT stiff skeleton. Then cast concrete of arch rib to form the composite arch rib. The last is to form the concrete-filled steel tube stiffened concrete arch bridges supported by the arch rib. Tiange Longtan Bridge, now it's being constructed. Its mass span length will be 600 meters. It will be the longest span of arch bridges after completed. Another challenge for suspension bridge is wind resistance stability. For long span suspension, which has poor structural stiffness, will vibrate easily in the wind circumstances. Tokamak suspension bridge got collapsed by wind in 1940, leading some aerodynamic measures, for example, guiding plate, coupling plate, rectifying plate, firing vertical and horizontal stabilizers. Aizhai Bridge in China is a steel truss suspension bridge. The mass span length is 1,228 meters. According to the wind tunnel test result, steel truss without aerodynamic measures cannot satisfy the demands of flatter shackling wind speed. So vertical and horizontal stabilizers was adopted in the bridge. Nansha Bridge is a integral flat steel box girder suspension bridge. The mass span length is 1,688 meters. For the bridge, after repeated wind tunnel test, it is found that the horizontal stabilizers arranged outside the wind fairings have a apparent effect on flatter stability of the box girder. Another approach is separate steel box girders. For Xihoming Bridge in China, the mass span length is 1,650 meters. Its flatter critical wind speed is very high, exceeding Grade 17 typhoons. So separate steel box girders are first adopted in the world. Wind pressure difference between top and the bottom surface is cut down by air convection through the opening between the two box girders, thus having good wind resistance performance. The third approach is adopting central buckles for main cables. For Ruiyang suspension bridge, whose main span length is 1,488 meters, dynamic characteristics without and with rigid central buckles for main cables are compared. It can be found that central buckles increase the stiffness and corresponding frequencies of the bridge. The fourth approach is using the external dampers. For Xihoming Bridge, vertical dampers are arranged between north tower and the girder. in the aeroelastic model test. Test results indicate that external dampers can increase the damping ratio of multiple vibration models effectively, avoiding vibration control. Another challenge for suspension bridge is the ultimate bearing capacity of main cable. Main cable is the main load bearing member for suspension bridge. With the increase of span length, tensile force in main cable also increase, requiring higher bearing capacity of main cable. If the size of the main cable is too large, it will be too heavy and unfavorable to structure wind resistance. So during the development of suspension bridges, material upgrade is the main key roles. The table shows the material. It has upgraded a lot from 100 years ago. Then for the cable stayed bridge, one challenge for the cable stayed bridge is the cracking of concrete girder. The early cable stayed bridges mainly adopted concrete girders, which were heavy and easily cracked. This table is the cracks of some cable stayed bridge in China. The approach is using the steel girders or steel concrete composite girder. For long span cable stayed bridges, steel girder or steel concrete composite girder are light, thus are able to span longer lengths and reduce material consumption of cables, towers, and substructures. The table lists the reasonable span lengths for cable stayed bridges with different girders. For concrete girder, the span is generally 200 to 400 meters. And for steel concrete composite girder, the length is around 640 meters to 540 meters. For steel girder, the span length is generally more than 450 meters. Third model bridge in Indonesia is a steel cable bridge. The main length is 434 meters. Its girder uses the steel concrete composite girder. For Nanjing Second Yangtze River Bridge in China, the main length is 628 meters. So integral flat steel box girder is adopted in the bridge. And for some bridges with low set-to-span ratio, hybrid girder will be employed so as to balance the self weight between mates and set span and avoid tensile bearings of set pairs. The table is some bridges, cable stayed bridges with the hybrid girder. For Edong Yangtze River Bridge in China, the main span length is 928 meters, and the side to main span ratio is 0.3. In the bridge,
you have another 3 minutes to go. 3 minutes, please.
Okay. So the bridge, for the bridge, the hybrid girder is employed. Another challenge is about wind resistance of girder. It's also with the help of structural and aerodynamic measures. The third part is technical innovations of long span bridges. First, the new material and technologies. Then some new structures. For new bridge types and structure systems, for beam bridges, we introduced some concrete and corrugated steel weber composite beam bridges. It is lighter and it has better seismic resistance performance. For the Jiyuke bridge in China, the corrugated steel weber composite beam bridge was used. Its mass span length is 125 meters. For arch bridge, the Zhijinghe bridge in China, the mass span length is 430 meters. The deck type concrete filled steel tube arch bridge is used for the bridge. For suspension bridge, self-anchored suspension bridge is a new structure type. Songyuan Zhenhe Bridge, the main length is 266 meters. And suspension bridge with multiple towers. For such suspension bridge with more than 2 towers, it has different. It is different from the 2 towers bridges. For Taizhou Yangtze River Bridge, it had 2 main spans. The bridge has 3 towers and 2 main spans. Modern capacity bridge, for Chongming Bridge, the main span length is 550 meters. And we adopt the consolidation system. It is the second longest capacity bridge of this structure system in the world. In the combination system bridges, including keep state and rigid frame combination bridge, and keep state and suspension combination bridge. This is some new construction methods. Last, the new series and calculation method. The last part is about prospective development of long span bridges. What's the longest span? I think that the span length of the bridge will increase in the future. For the arch bridge, 800 meters. For capacity bridge, 1,500 meters. And for suspension bridge, 4,000 meters will come into being in the near future. The second one is about building material with better performance, including high performance and light weightage material. For design, performance-based design theory, automatic drawing, fast optimization, and numerical simulation. Also, robustness of bridge structure will be more important in the future. For construction, including the industrial manufacturing, assembly construction, intelligent construction equipment, larger and heavy duty construction equipment, rapid construction, 3D printing. In fact, for the Nanjing Fifth Bridge, it's a capacity bridge. More than 80% works was finished in the factory. Then the maintenance and repair, intelligent detection, automatic monitoring, intelligent solution. Okay, that's all. Thank you.
Thank you very much, Mr. Guo Binli. I believe there are so many high-tech bridge construction in China, because we know that your which technology in China is very advanced. And you have built so many long span bridges with variety of construction. So actually in your presentation, there are so many interesting information, but unfortunately the internet connection is not very good. However, for the participant, we could give the the soft copy of the presentation later on will be made available by the committee. So with that, again, thank you very much, Mr. Go Bin Lee. Then we will continue with our last speaker, our friend from PT Wijaya Karya, Pak Ahmadi Tri Cahyono. Pak Ahmadi Tri Cahyono, Bapak juga 30 menit ya Pak ya?
Ya Pak. Oke baik, terima kasih Pak Wendy. Selamat sore, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, gentlemen, ladies and gentlemen. Yang terhormat Pak Bambang, Chairman daripada Badan Kejuruan Sipil khususnya PII. Kemudian previous speaker, very amazing one ya, Mr. Andrea, Mr. John Anderson, and last one, Mr. Go Bin Ling from China. It's wonderful presentation, especially for bridge from China. Baik Pak, kita yang dari Indonesia juga mencoba untuk menyajikan sesuatu. I will show you something, especially for construction of new bridge in Indonesia. Oke, nama saya Ahmadi. My position now as Head of Engineering PT Wijaya Karya Persero Tbk, state-owned company yang dari Indonesia. Now I will start from some of the iconic bridges in Indonesia. In the presentation showing the some new bridges, including Otekam. It is done by BP, and from location at Papua, Tayan. This is almost same with Chao Tiangmeng bridges, which already explanation by Mr. Go Bin Lee. Jembatan Merah Putih yang di Ambon, ini oleh Wika, kemudian ada beberapa balerang dan juga some of cooperation together with Chinese company with same with what Pak Mr. Go Bin Ling explanation. Kita bekerja sama untuk jembatan Suramadu. Okay, first of all, I will talking about our company, especially PT Wijaya Karya Persero Tbk is a state-owned company, and this is our overview. Now we have a vision and vision and mission. I think I will skip on this issue, but the important one is I will introduce my BOD, Board of Direction. This is a young gun from Indonesia, led by Mr. Agung Budi Waskito as a President Director, and we have 3 Operation Director. Mr. Hananto Aji is one Director Operation 1, Mr. Harum Ahmad Zudi is Director Operation 2, and Mr.
Ahmadi,
3. And then some of the support director.
Presentasinya Pak Ahmadi? Enggak.
Pak?
Slide presentasinya ada.
Sudah bisa, Pak? Yeah, I think we going to business line of Wijaya Karya. First is upstream and midstream, and also we also focus on the downstream. I will skip this one. Ini bisa kelihatan ya, Pak?
Ya, bisa.
Okay. So now related with the title of our presentation, special portfolio gallery of Wika, we want to showing 3 iconic bridges which already done or finished, such as Semanggi Interchange, and then the second one is and the last one now ongoing project is Alalak Bridge. In this presentation, I want to show WICAS capability project management and also leadership, because beside we focus on the technical solution for the how to finish the project for bridge especially, we also develop leadership for the people of Wijaya Karya. The first one is we want to talking about the Semanggi interchange. This is a very iconic bridge, Semanggi. This one of special. The previous one is Semanggi, designed by built during first President Soekarno era, and then now Mr. Jokowi want to develop with the new one, and of course most unique, for example, information, the bridge type is concrete spoke girder, and then cost around 24.8 million US dollar, and especially for time, this is very tight schedule, and then also contract system is lump sum one. And design and build, that means designed by Wijaya Karya, and also engineering, procurement, construction, also testing. Alhamdulillah, we also achieve the target as this is a photograph during our documentation during Mr. President, Mr. Jokowi meresmikan jembatan ini. Pada saat itu Mr. Jokowi push us sampai dengan peringatan 17 Agustus 2017 kalau nggak salah, 17. Jadi ini luar biasa kita push gitu. Dan ini merupakan one of the icon of Jakarta. And then pekerjaannya, metodenya adalah satu pekerjaan dengan metode bridging using the spoke girder system with the longes, especially curve span, with the longes curve span around 80 meters, and then also this is first method, first type of the bridge at Indonesia. This is our point of view from top. We can show that this is model of the Semanggi Bridge. Erection work of the concrete spoke girder is this is a very unique one, because we should be concerned about the banana effect, because part of the bridge is curve type. Erection work of the concrete spoke girder with semi-balanced cantilever system. Semi-balanced cantilever system, the segment spoke girder precast installation method combine the full span system with the cantilever balance system. The principle of counterweight for the erection span using the lifter is done first with the full span method. The proposed full span method using shoring and crane tool. So during the installation for the Semanggi Bridge, we focus on the banana effect. You know, this one is the part of the bridge is curve one. This is very dangerous one because of the centrifugal force. Erection work of the concrete spoke girder, you can we combine using the construction using the shoring, and also some of the pouring cast in situ such as the pier. One of the challenge we should be also consider about the utility under the existing site, because you know Jakarta previous condition or existing condition is not managed well. So we should be aware to underground utility and another thing. So this is why during we construction this job, we should be very what is that, concerned about the jalur kabel, for example, cable line, and then we should be modified and using some equipment to identify what kind of the underground facility existing to avoid any possibility problem, such as kabel listrik from supply by PLN. The special one is when we talking about the V column work. One of the column model is like V. So this column will work together when the beam already installed, already concrete. Yeah. But before that, we should be using the strand to what is that, to avoid any problem damage for the column. So that's why we using install the bracket and also using the VSL sim with some previous presentation explain using the cable or strand, something like that.
Pak Ahmadi, maaf ya, Pak Ahmadi.
Iya Pak.
Jadi kan ini kan Bapak pakai presentasi dari sebagai background. Ini mungkin di belakangnya ada multimedianya Bapak ya. Jadi tidak pakai share screen. Sehingga beberapa teman ini dari partisipan kesulitan. Apakah Bapak bisa pakai share screen supaya lebih mudah?
Oh boleh Pak.
Ya, kita tunggu.
Share screen.
Barangkali
dari sini bisa ya?
Ya, kalau share screen di situ ya. Jadi lebih besar gambarnya agak mudah. Nah, itu lebih bagus. Coba diklik di share screen barangkali. Kalau di full screen kan. Nah, itu lebih bagus. Ya. Udah kelihatan ya, teman-teman? Yang lain?
Ini kelihatan, Pak ya?
Nah, ini bagus.
Sudah.
Ya.
Oke Pak, kalau audionya bahasa Indonesia aja biar lancar Pak ya.
Iya betul Pak.
Oke Pak, baik, salah satu kolom yang kita harus selesaikan adalah yang bentuknya V ini Pak. Jadi untuk kita bisa mengefisiensikan kita shoringnya, jadi kita tahan dulu Pak dengan menggunakan strand di tengahnya itu sebelum kita pasang di bagian atasnya. Selanjutnya karena ini ikonik, maka di desain itu membuat parapetnya dengan memiliki
yang lain tolong di mute. Pak Ahmadi silakan Pak, diteruskan. Di unmute.
Selanjutnya ini adalah beberapa gambar yang kita lakukan, ada beberapa memang yang kita precast, ada beberapa yang kita cast inside dengan memperhatikan schedule yang ada sehingga kita bisa mencapai waktu yang ditetapkan. Nah, beberapa hal yang khusus di proyek ini adalah penggunaan LRB, bukan menggunakan elastomer bearing biasa, tapi kita menggunakan lead rubber bearing itu Pak. Jadi ini memiliki kelenturan sehingga mampu menahan gempa, dan beberapa studi kita lakukan, ada beberapa kurva historik dari LRB yang bisa kita lihat di materi presentasi itu, dan ini menjadi satu pilihan yang menjadi menambahkan ketahanan daripada jembatan Semanggi itu sendiri. Kemudian yang kedua adalah Tumbang Samba Bridge. Ini alhamdulillah kemarin kita selesaikan dan mendapatkan apresiasi di Instagramnya Pak Jokowi Pak. Jadi ini merupakan salah satu juga ikonik jembatan yang kita selesaikan, yaitu ini sebenarnya jembatan ini mirip dengan disampaikan oleh Mr. Go Bong Lin tadi, ada di Cina juga mirip persis. Cuman ini jembatan ini memiliki satu situasi desain yang lebih unik, di mana penggantungnya ini berupa net gitu ya. Artinya dia tidak lurus Pak, tetapi miring-miring yang luar biasa. Dan dengan uniknya ini merupakan apa namanya, termasuk yang kita pilih menjadi juara di internal Wika juga, dan sekarang kita coba akan dorong mengikuti beberapa lomba untuk mendapatkan pengakuan bahwa khususnya Indonesia ya mampu mendesain jembatan yang cukup unik, mana ini adalah arch bridge yang memiliki suatu keunikan tersendiri, tidak hanya secara desain tetapi juga bagaimana kita mengangkatnya. Ini kontraknya juga lamsam, ini juga design and build, sehingga seluruhnya kita kembangkan, dan yang paling melegakan bahwa ini adalah semua produksi dalam negeri. Jadi hanya penggantungnya saja yang kita produksi kita ambil dari Eropa, tetapi untuk produksi jembatannya kita buat di Majalengka, dan pernah dikunjungi oleh Pak Basuki, Pak Menteri pada saat kita melakukan pre-assembly di sana. Satu hal yang cukup perlu saya sampaikan di sini adalah bahwa pada saat pelaksanaan pekerjaan ini kita menghadapi situasi banjir Pak tahunan, karena memang sungai di bawahnya itu adalah sungai-sungai yang masih perlu perhatian kita semua, di mana penerbangan liar mungkin masih cukup tinggi, sehingga debris-debris itu yang pada saat banjir selalu mengancam pada saat pelaksanaan. Kemudian pada saat 2019 kita ketemu kendala, yaitu adanya kabut asap juga, ini satu kendala juga yang kita hadapi. Kemudian juga beberapa kesulitan-kesulitan lain, seperti yang tadi saya sampaikan, logging waste atau debris itu juga ya sosial terutama. Inilah yang menjadi unik kalau membangun jembatan di Indonesia. Pada kesempatan ini saya ingin sampaikan bahwa jembatan Tumbang Samba ini dibangun tahun 2017. Seperti yang saya sampaikan bahwa ini Pelengkung Baja Modified Network Tight Arch Bridge, yang merupakan jembatan pertama yang dibangun dengan metode full span lifting dengan synchronize 4 titik. Jadi yang ini menjadi menarik karena memang jembatan ini kita angkat bagian tengahnya secara penuh gitu. Nah, oleh karena itu pada kesempatan ini saya menyampaikan terima kasih kepada Pak Imam Jarkasi ya sebagai yang paling aware nih. Kemudian ada KKJTJ, ada Satker, ada juga Balai yang membuat jembatan Tumbang Samba ini sukses Pak. Jadi sekali lagi terima kasih dan salam hormat setinggi-tingginya. Kemudian ada beberapa khususnya di desain hanger saling bersilangan ini mengakibatkan distribusi gaya, momen, dan lintang tersebar merata. Dan ini kalau kita bandingkan dengan desain-desain jembatan yang sejenis, yang mirip, yang bukan metode ini kita bisa mereduce berat total dari kalau kita reduce 30 sampai 40% ya Pak, Bapak Ibu, sehingga jembatan ini cukup ringan untuk diangkat, tetapi memang memerlukan ketelitian dan kemudian teknik-teknik yang baik serta assessment pada saat pre-lifting itulah yang menjadi perhatian luar biasa, karena pada saat 2007 di tengah gencarnya kecelakaan jembatan Pak, jadi semuanya menjadi khawatir bagaimana ini jembatan yang ringkih gitu kelihatannya akan diangkat dengan menggunakan jack 4 poin lifting dengan secara sinkronis. Dan sekarang ini kita siapkan hal yang sama Pak untuk rule daripada stadion JIS Jakarta International Stadium. Kita juga akan mengangkat yang sama tetapi menggunakan 8 poin, masing-masing poin itu ada 2 titik sehingga ada 16 jack yang kita gunakan, dan merupakan kerjaan yang harus fokus, di mana kita harus menjamin bahwa pergerakan jack itu sinkronis bareng. Ini adalah tampak dari atas sebelum posisi diangkat, di mana Tumbang Samba ini haruslah tetap stabil saat diangkat. Oleh karena itu titik angkatnya harus berada di atas titik berat jembatannya. Jadi kita cari dulu titik beratnya, kemudian titik angkatnya harus ada, perhitungannya harus di atasnya gitu, sehingga menggantungnya lebih stabil. Kemudian percoba di mana model atau start jembatan ini ngangkat adalah kita angkat dulu setinggi 10 cm untuk menjamin seluruh parameter-parameter yang sudah kita tetapkan itu tercapai dari sisi kestabilan, dari sisi pressure oli di hidrolis dan lain sebagainya, sehingga kita bisa memastikan semuanya manakala seluruh parameter yang ditetapkan yang sudah disetujui oleh KKJTJ, kemudian Satker dan juga balai yang menjadi checklist itu terpenuhi, maka selanjutnya dilakukan step by step checkingnya. Seperti ini adalah gambar tampak samping. Tentu yang di bawah itu adalah tempat assembly dulu sebelum diangkat ke positioningnya di atas. Selama assembly juga ketemu beberapa kendala termasuk juga debris-debris yang lain sebagainya yang memang harus selalu dimanajemen dengan baik.
3 menit lagi.
Hal-hal yang lainnya kalau kita bagi tahapannya ada tahapan yang pertama preparation ya, kemudian yang kedua adalah tadi seperti saya sampaikan diangkat 10 cm ditahan 1 jam untuk melihat segala sesuatu parameternya, kemudian baru lifting dan kemudian memasang di pojok kanan kirinya untuk dudukannya, dan selanjutnya kita sama-sama pastikan setelah itu kita rilis setelah semua selesai. Saya lanjutkan untuk Alalak Bridge. Alalak Bridge ini ada di Banjarmasin. Kalau Bapak Ibu sekalian tindak atau jalan-jalan ke Banjarmasin akan melihat sebuah jembatan.
Pak Ahmadi, maaf ya, 3 menit lagi Pak Ahmadi.
Ya Pak, kenapa Pak?
3 menit lagi ya.
Ya baik. Ini adalah Alalak di mana ini memiliki satu karakteristik sendiri di mana pilionnya asimetris Pak, melengkung, dan ini merupakan tantangan tersendiri. Kemudian tantangan kedua adalah mesh konkrit. Seperti biasa kita how to avoid the crack di konkrit ya, sehingga kita melakukan upaya seperti pendinginan dan lain sebagainya, sehingga kita bisa menjamin bahwa mesh konkrit ini bisa berjalan dan menghasilkan sesuatu yang masif dan solid, tidak terjadi crack. Bagaimana kita mengatasi perbedaan suhu di luar dan di dalam konkrit yang tidak lebih dari 25 derajat Celcius, karena ini kan hot weather konkrit istilahnya. Jadi kita mengembangkan beberapa, memang ada yang bagaimana treatment after konkrit atau kita menggunakan pendingin di dalamnya. Kita menggunakan pendingin di dalamnya. Terus kemudian ini adalah foto-foto yang Alalak Bridge. Ini foto-fotonya, dan ini kita kontrol temperatur di dalam konkritnya sehingga kita bisa menjamin bahwa mesh konkrit yang dilakukan menjadi baik sesuai dengan kriterianya. Nah, yang paling penting pada kesempatan ini ingin saya sampaikan bahwa Wika memiliki readiness ke depan untuk membangun jembatan-jembatan modern yang seperti disampaikan para presenter sebelumnya, baik seperti yang di Cina maupun yang di Eropa tadi, karena kami memiliki satu adalah knowledge dan experience. Kemudian pada kesempatan ini kami tidak hanya knowledge dan experience, tetapi juga mengembangkan project management juga leadership Pak, orang-orangnya Pak, sehingga kita juga siap secara tool dan juga secara personil. Kemudian kami memiliki beberapa perusahaan subsidiary yang mampu mendukung terselenggaranya proyek-proyek yang khusus, yang besar, seperti misalnya Wika Beton, kemudian juga Wika Ikon, pabrik baja kita memiliki kemampuan 60.000 ton per tahun. Kemudian saat ini kita para CEO Wika telah memutuskan proses digitalisasi digital transformation. Maksudnya tidak hanya membuat digital proses saja Pak, tetapi deep insight, membenahi semua bisnis model sehingga kita menjadi lebih efisien menggunakan seluruh yang ada saat ini. Kemudian mengembangkan strategi partnership seperti kita sudah yang lalu seperti Suramadu dan juga Tayan, itu kita join together dengan Chinese company. Ini adalah salah satu contoh tempat leadership training kita, Pak, training ground untuk leadership. Kita membangun di Bogor khusus yang saat ini juga digunakan Kementerian BUMN sebagai training ground untuk leadership. Kemudian ini adalah Wikaton, kami memiliki 0,5 juta ton per tahun, Pak, produksi konkret, Pak. Jadi tersebar di seluruh Indonesia dengan kemampuan yang besar, sehingga apapun yang ada tantangannya di seluruh Indonesia, insya Allah kita siap. Kemudian Wika Icon Factory tadi yang saya sampaikan, kita baru menyelesaikan pabrik besar, Pak, di Majalengka, 60.000 ton per tahun, sehingga kita tidak hanya mampu membackup infrastruktur di Indonesia saja, tapi juga saat ini kita bekerja sama dengan Materi, teknologi yang sistem bridge yang pakai PIN, Pak. Kita melayani ekspor ke Filipina. Seperti ini. Jadi kita bersama dengan satu perusahaan Prancis, ini adalah merupakan strategi partnership kita dalam mengembangkan kemampuan kita di teknologi jembatan. Ini adalah salah satu kemampuan kita di software, Pak. Kita BIM. Tidak hanya dengan Autodesk, tapi juga dengan Bentley, sehingga kita merupakan BIM yang open, Pak, yang bisa bekerja dengan berbagai platform. Dan ini beberapa proyek yang tol Serpan, kemudian proyek yang lain, tol yang lain kita mengembangkan dengan BIM, sehingga kita bisa mendapatkan efisiensi, kecepatan keputusan, dan deteksi dini terhadap beberapa problem yang mungkin saja terjadi saat pelaksanaan. Saya rasa itu, Pak, yang bisa kami sampaikan, bahwa memang Wika saat ini salah satu state-owned company yang ready to go, Pak.
Yes.
Tinggal nanti makanannya seperti apa tergantung ke depan kebijakan pemerintah. Demikian yang bisa saya sampaikan pada kesempatan ini. Kalau ada kekurangan mohon maaf. Thank you.
Terima kasih. Thank you, Pak Hamadi. Ini very also sama interestingnya dengan pembicara-pembicara sebelumnya. In fact, Wika, the leading construction company in Indonesia, especially in bridges, already applying some modern technology in bridges. But before we continue with question and answer, but let me just very quickly just try to summarize the presentation from the first speaker up to the last speaker in bahasa. So presentasi yang pertama tadi dari Pak John itu menjelaskan mengenai cable stay yang alignment-nya sekaligus curve melengkung ya, dan strukturnya itu kombinasi antara kabel stay biasa dengan beton precast konkret, jadi extra dose. Jadi di situ mungkin uniknya yang beliau sampaikan, sekalipun tadi saya sampaikan panjangnya juga tidak terlalu signifikan, tentu sekitar 300, tetapi dari sisi keruwetan teknologi seperti itu, karena dia harus mengakomodir jalan kereta yang melengkung, itu yang pertama. Yang kedua tentang dari Andrea Mordini, ada beberapa, tapi antara lain yang movable bridge, ya, bridge yang naik turun seperti kita di jembatan mana itu ya, Palembang itu ya, seperti gitu. Tapi ini jembatannya bentuknya beda, untuk supaya kapal bisa di bawahnya bisa lewat. Itu cukup besar, 87 meter katanya span-nya, supaya lebar kapal bisa lewat. Itu dibuat di Amsterdam, dia bilang. Dan juga ada beberapa lagi proyeknya dia, antara lain di mana, di Doha kalau nggak salah. Kemudian dari Pak Guo Binli itu menjelaskan sebetulnya cukup komprehensif dari awal-awal perkembangan teknologi jembatan sampai yang saat ini, bahkan beliau mengantisipasi terakhirnya beberapa teknologi ke depan, baik dari sisi teknologi, dari sisi metode, dari sisi cara perhitungan, maupun dari sisi new material yang emerging yang bakal akan berdampak kepada kemajuan kita dalam teknologi jembatan pada khususnya. Cuma memang tadi agak terganggu dengan internet connection. Nah, yang terakhir, yang keempat, yang mengembirakan kita dari Wijaya Karya Pak Ahmadi menjelaskan ada paling nggak ada 3 ya yang disampaikan tadi, yang proyeknya yang ikonik. Yang pertama di Semanggi, jembatan Semanggi 2. Yang berikutnya adalah jembatan Samba yang tadi dikatakan unik, jembatannya arch begitu, gantung, tetapi hangernya tidak lurus, melainkan hangernya seperti bersilangan seperti itu. Dan terakhir juga jembatan yang Alala Bridge, yang kalau nggak salah juga itu cable stay, tapi juga bentuknya arch yang melengkung. Jadi kurang lebih seimbang juga dengan apa yang dipresentasikan oleh presenter yang pertama tadi. Dengan begitu saya buka pertanyaan. Ini saya lihat di chat belum ada terlalu yang bertanya. Jadi kalau dibolehkan sama panitia ini, saya persilahkan bagi ibu bapak yang ingin bertanya langsung. Silakan. Halo? Ya, silahkan. Siapa yang tidak bisa lihat? Siapa yang ingin bertanya? Sebutkan namanya. Pak siapa? Pak Ayudin. Pak Ayudin. Silakan Pak. Coba agak dekat dengan mungkin suaranya supaya bisa lebih jelas. Oh ya Pak ya. Of course, I would like to thank for all the speakers today. Talking about saya sih tidak bisa dengar, nggak tahu yang lain. Apa pembicara speaker bisa dengar nggak?
Nggak kedengaran.
Nggak kedengaran ya.
Ya, karena hujan keras itu Pak.
Kalau nggak bisa suaranya tidak terdengar, mungkin lewat di type aja Pak, di chat, soalnya suaranya Bapak nggak bisa terdengar. Atau Bapak lebih dekat dengan speaker.
Oke.
Dengan mikrofonnya maksudnya.
Bagaimana Pak?
Suaranya tidak terdengar, mungkin Bapak bisa.
Kedengaran Pak ya?
Lebih bagus sekarang.
Ya, sekarang.
Ya.
Ya.
Sudah boleh Pak?
Silakan Pak.
Ya silakan, udah kedengaran. Coba tes.
The first, I would like to thank for all the speakers today, talking about the progress of the bridge model. And I would like to thank for Simon Civil Professional Agency, Indonesian Engineers Association, Bapak Profesor Bambang Burikno, and thank you very much for Habibie Rasak and moderators, Bapak Insinyur Wendy, the IT. I feel the topic is very interesting today about the bridge models, cable stay, and I think must like by engineers, the governments, and the private sector, because cable stay bridge model can be designed with a long distance. And in terms of aesthetic, it's very beautiful. But allow me to ask for
berapa kira poinnya kalau sertifikat Nabila pengantar?
Sisi infrastruktur teknologi group talking about performance improvement of long span bridge. My question, how to repair of long span bridge that has a structural damage. For example, experience porous concrete or hollow concrete, and how to repair of long span bridge if it experience deflection of the vehicle floor or experience deflection in the bridge foundation. I think the correct method is needed to the bridge doesn't collapse. I would like to ask for SMAC 2 one more question for Bapak John Anderson from SMAC International. Before I ask for you, I would like to share information that in Indonesia, that a number of areas in Indonesia experience extreme weather, which result in hydrometeorological disaster, such as floods, landslides, and strong winds, even earthquakes. So my question, can the cable stay bridge construction be applied in Indonesia? Because extreme weather, how intense of the strength, over of the strength, especially in cable stay side, if one day there is extreme weather, by getting a pressure, a strong winds, or a crosswind. Thank you. Terima kasih, Bapak Moderator. Mohon maaf, hujan keras di Makassar, Pak.
Baik, Pak.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Ada lagi pertanyaannya? Kita kumpulkan dulu, mungkin 3. Silakan Bapak-bapak, kalau ada yang tanya mungkin bahasa Indonesia juga nggak apa-apa. Oke, kalau sementara belum, jadi saya tadi dengarnya on off ya, mohon maaf kalau kurang ini. So the question is one from Dr. Ayudin. One is how to repair the concrete bridge if there is any damage, and the second about if there is also a deflection. I'm not sure whether it's a deflection in the concrete base or on the cable stay, but it's assuming it's applied to any bridges. If there is a deflection, how we fix it? And the second question to Mr. John Anderson, if I'm not mistaken, is how the same technology could stand with or for the extreme weather. Like for instance, in Indonesia, the heavy rain could cause the landslide, strong wind, the crosswind, etc. Something like that. So maybe this also, the question is a general question, maybe can be answered by all the speakers according to their expertise and their experience. Setuju ya Pak Ayudin begitu ya?
Yeah. If getting a pressure, a strong winds,
Yes.
or a crosswind.
Yeah.
Especially of the state. Ya,
Okay.
saya kira begitu maksud saya.
Thank you, Pak Ayudin. So, John Anderson and Andrea and Mr. Guabini or Pak Ahmadi, while we waiting for another question, we can start with answering by the first question first. John.
Okay. Just I might just start with the question about the suitability of cable stayed structures for extreme weather conditions. I think the important thing to note with cable stayed structures is there's a high degree of redundancy. Obviously, you have multiple cables carrying the load. And generally, when you're designing a cable stayed structure, you've got to design for cable failure. That might be one cable, 2 cables. So you have to account for the fact that 1 or 2 cables may, there may be a fire event. There may be a need to replace it just because of a durability issue, a long-term durability issue. But generally, cable stayed bridges are designed so that you can replace those cables and you can keep the bridge open while you do replace those cables. Just in terms of extreme events, obviously extreme events are not isolated to Indonesia, and there are many cable stayed bridges around the world. Generally, with any long span structure, you have to test the aerodynamic behavior of that bridge, and then you would have to wind tunnel test that bridge during construction and in its permanent state. And there are various techniques that you can use in terms of the profiling of the deck or the insertion of baffles underneath the deck to control the aeroelastic response of the bridge. And as I say, you even have to do that during construction, because while you're cantilevering the bridge out, the bridge may be subject to an extreme event. So I think designers do have in their arsenal the ability, or to consider and design for those events. In the Philippines, for example, you have to design for extreme earthquake events, and there's sort of basic design techniques, which is deflection. You define for a displacement rather than a strength, and you allow the structure to hinge. And in a cable stay structure, you can do the same. It's a little bit more complex in terms of the seismic response of that structure, because it's not a linear response. It's a very a cable stay bridge is essentially behaves non-linearly. But I think the point is we can design for it, and we use probability. So we look at extreme events, and we use probability to project the possible load effects that there might be on the bridge. So I do think that cable stay bridges can be used in Indonesia. There's no doubt about that. And then just to go on to the repair of perhaps long span concrete bridges. Again, with cable stay structures, obviously you've got the redundancy with the number of cables. With a cable stay structure with a flexible deck, it's relatively easy to change the geometry, to go back and to re-stress the cables. You can do that on a flexible deck. If you have a stiff deck, you would have to go back, physically jack the bridge up, then shorten the cable to change the geometry of the bridge. The other thing is you can put in continuity PT, pre-stressing, which, external pre-stressing can be used to try and affect the change in the geometry. So often where we have damaged structures, we retrofit external post-tensioning to the structures. And generally access to those points is off the deck. We create either under deck, scaffolding that comes from the top of the deck underneath the deck, or we even use under deck inspection units to go in and give access to the soffits of the deck. So there are definitely strategies that you can employ to repair and look after concrete sections on long span structures. Thanks.
Thank you, John. Before I forget, let me reiterate your explanation in Bahasa.
Yeah.
For the benefit of all the participants. So basically yang Pak John katakan bahwa cable stay itu sebetulnya mempunyai redundancy yang besar. Jadi kalau misalnya dalam repair atau misalnya salah satu kabel putus atau salah satu kabel kendor, itu dipastikan bahwa perbaikan masih bisa dilakukan tanpa mengganggu operasi jembatan. Jadi dengan satu atau dua kabel misalnya yang tidak bekerja, itu masih bisa jembatan masih bisa beroperasi. Itu katanya begitu. Jadi orang mendesain kabel stay katanya dia bilang gitu, redundansinya besar. Kemudian kalau mengenai dari ekstrim event ya, jadi cuaca ekstrim ataupun kadang-kadang yang ekstrim seperti gempa bumi segala itu memang masuk di dalam beban yang diperhitungkan, beban-beban rencana yang diperhitungkan. Bahwa bagaimana responnya terhadap beban-beban tersebut, sebetulnya dalam desain itu dites di laboratorium terowongan angin atau di wind tunnel. Di Indonesia itu kita punya wind tunnel besar di BPPT di Serpong. Itu bisa melihat dari karakteristik dari aeroelastik, dari respons dari kabel stay. Kemudian kalau ada yang kendor tadi, misalnya decknya turun gitu, bisa dimainkan si kabelnya ditarik, diturun, atau juga kalau decknya itu berupa beton, itu bisa juga dilakukan dengan post tensioning gitu, di jack dan di post tensioning. Kurang lebih pembahasan umumnya seperti itu gitu. Mohon maaf kalau ada yang kurang. Andrea Mordini, you want to respond with the same question?
Yes, for sure. I think John has already given quite a comprehensive answer. I fully agree with what he said. In general, cable stay bridges are quite flexible structures. So this is actually one strong point because this flexibility of the structure allow, for example, the question was talking also about settlement. So for example, if you have some differential settlements and the span usually is long, the deck is usually flexible. So the deck is quite able to take these differential settlements and differential rotation quite easily. On top of that, if the question was also mentioning deflection, so as John already said, you can play quite well with retensioning the cables to reobtain your shape. Sometimes it happens, for example, that with already existing bridges, for example, the effect of creep and shrinkage was not properly considered, and then you have to readjust the cables to reobtain the optimal shape. Regarding wind, I just want to mention that sometimes when you have systems of cables, you might have induced vibrations on the cable themselves. We have seen in the past some examples, especially when there is the combined effect of wind and rain. And those effects are actually not always easy to capture from the analytical point of view. However, we can intervene also in those cases. And some ways, for example, to correct this kind of vibration, for example, is the installation of dampers, or the installation of cross ties, which are basically transversal cables that connect the mainstays, and this makes the system moving and behaving as a connected net. And so the frequencies of the cables, which are each of them different, are connected, and so there is a combined movement and combined stiffness. Usually the architects don't like this. Sometimes you are forced to, and if you see that the ties are usually very small, and you try to minimize the visual impact, but sometimes you are forced to install them. Dampers are another way. However, usually you install the dampers at the deck, and the deck you have a quite small amplitude of the vibration, so it's not the best position, the most effective position for the dampers. So you try to install as high as possible so that you have a more wider amplitude. So it depends on the severity of the event, but yeah, those are mainly the two countermeasures that you can consider.
Thank you, Andrea. Again, I would like to translate to my colleague in the
Sure.
house. So Pak Andrea basically setuju dengan apa yang dikatakan oleh Mr. John Anderson. Hanya beliau menambahkan aja beberapa. Yang pertama kaitannya dengan kalau ada vibrasi yang tidak terkontrol, katakanlah terlalu besar, maka katanya ada dua hal yang bisa dilakukan. Yang pertama menambah damper di decknya, nambah damper, atau katanya menambah transfer cable yang menghubungkan antar kabel, dengan demikian bisa mengurangi perbedaan frekuensi antar kabel. Persis saya sendiri saya belum pernah lihat, tapi katanya Mbak Andrea bahwa ini secara teknis memang lebih mudah, tetapi biasanya arsitek nggak suka karena jadi tanda petik merusak appearance dari kecantikan dari kabel C. Salah satu keuntungan dari kabel C dan kabel jembatan gantung itu kan adalah bentuknya yang cantik gitu. Oke, kita mungkin ada Pak Mr. Go Bin Lee, you would like to respond to that? Kita nggak dapat respon dari Mr. Go Bin Lee. Mungkin lanjut ke Pak Ahmadi.
Ya Pak.
Silakan Pak Ahmadi.
Ya, saya rasa semua tahu ya Pak, kabel stay ini sebuah hasil inovasi yang luar biasa. Sehingga kita bisa mengambil manfaat dari kemampuan, flexibility daripada kabel stay. Tapi saya lihat, saya setuju dengan yang penjawab pertama Pak, dua orang tadi, Andrian dan satunya tadi, Anderson. Bahwa memang kalau kita kan melihatnya sederhana Pak, terutama ya kita sudah wajib mampu menerjemahkan kebutuhan engineering terkait dengan kabel stay-nya. Very clearly proposed lah. Kemudian kita mencoba mencari mana pabrikan yang mampu memberikan solusi atas kebutuhan kita. Nah kalau seperti itu kita akan melihat beberapa saja Pak. Pertama adalah code and standard. Kemudian yang kedua adalah kita kadang-kadang kalau ingin tahu lebih dalam, kita mencoba melihat sekali lagi ITP yang dikembangkan oleh pabrikan atau produser, di mana ITP ini merupakan satu upaya kita untuk mengecek, yaitu inspection test plan mereka, bagaimana mereka mampu menjawab kebutuhan teknisnya dengan tes-tes yang dilakukan, apakah sesuai dan lain sebagainya. Dan sisi lainnya adalah bagaimana upaya-upaya maintenance, reliable and maintenance. Hampir semua jembatan yang sangat mahal yang menggunakan kabel stay senantiasa mengembangkan atau khususnya manajemen perawatannya ini, maintenance and reliable. Sehingga ini merupakan bisa dikatakan preservation isu lah Pak. Jadi di mana preservation issue adalah upaya-upaya terencana dalam menjaga kualitas produk tersebut sesuai dengan yang direncanakan gitu. Sehingga kita memiliki sebuah develop schedule, develop activity, develop semua peralatan penunjang, early identification dan lain sebagainya. Sehingga hal-hal yang mengkhawatirkan bisa kita antisipasi selama atau selama umur fungsi daripada struktur yang kita harapkan bersama. Mungkin itu Pak tambahan saya Pak.
Oke Pak, terima kasih. Ini ada yang ingin bertanya, silahkan Pak, siapa ini? Pak Hamonangan dan Pak Hamzah. Silahkan Pak Hamonangan dan Pak Hamzah. Pak Hamonangan dulu barangkali. Halo? Pak Hamonangan? Atau Pak Hamzah? Atau siapa yang ingin bertanya? Ini saya nggak dapat lihatnya. Atau Pak ini, Pak Prastiwo Anggoro ingin bertanya?
Yeah. Okay, yeah, Pak Wendy, thank you. Yeah, firstly, maybe I will sharing in Kepri, government already planned to make one bridge. The span is around 7 kilometers. Go through the Batam Island, then connect it to the Bintan. So in here, I saw they plan to vertical clearance around 40 meter, because there is existing what you call it, transportation sea crossed by their area. Maybe I would like want to hear from the all the expert here. What is the best type of the bridge there? Because other than vertical clearance, then we know also the winds, the wind condition over there is quite big as well. But of course, for this, in the Caprice there is no earthquake. I think it's quite small. But these two is the important issue we need to face before we construct this bridge there. That's all, Pak. Maybe from me. Maybe also from Wika, because Wika also I saw there is a plan in Batam ya Pak ya, for this CTL ya, if I'm not wrong ya Pak ya. Yeah. This one nearby my house also there. Okay Pak. Thank you Pak. Pak Wendy. Ya.
Terima kasih Pak Prasetyo Anggoro. Tapi Pak Prasetyo ini supaya apa namanya presenter lain yang belum tahu detailnya bisa respon dengan proper, mungkin selain apa tadi 7 kilo itu 7 kilo satu span, apa dibagi berapa span atau kemudian kedalamannya berapa biar beliau-beliaunya itu bisa ngira-ngira gitu.
Correct Pak Wendy. I'm sorry because it's totally divided by 2 span ya. There is one island in between Batam and Bintan. So maybe mostly 2, if not wrong, 2 kilometer and 4 kilometer like that.
So you mentioned that the 4 kilometer, one of the longest span is 4 kilometer free span.
Yes, Pak. Around there. Around there.
This is thank you, Pak Prasetyo. Mr. John and Mr. Andrea and Mr. Gobini dan Pak Ahmadi. One of the participants raised the question that in Indonesia, in the near future, plan to build a very long span bridge connecting Batam Island and Bintan Island. Is the island very close to Singapore. So the total distance between Batam Island and Bintan Island about I think about 5 or more kilometers, or more, even more. In the middle, somewhere in the middle, there is a small island. It can be used as the first landed. So basically, the bridge will be divided into 2 long span. One span 2 kilometers, and the other span could be up to 4 kilometers. So his question is there any suggestion what kind of technology of the bridge that more you think is suitable with this kind of condition? Pak John Anderson and Andrea Morini and Guam, perhaps you would like to respond in a very general, perhaps. Thank you.
Yeah, thanks. I think the longest span structure that we've built so far is I'm not sure, but I think it's probably close to 1.8 or 1.9. I'm not sure, but it would be a suspension bridge. But I think that's the upper reaches of our technology at the moment. Would be that sort of span length. You know, typically when you're talking bridges of that length, you will have shorter spans involved and then navigation channels to allow shipping to pass. That's typically the approach that's taken. You know, some of these long bridges that you see across these big rivers in India, which are a couple of kilometers long, often they have extra those spans so that you can have constant deck sections, 100-meter spans, and rapid construction. But you know, it sounds like a very interesting project, but there's so many influencing factors in the decision making that you'd have to consider in terms of the optimum span length. But there's, you know, I think that's probably a big task for any designer. But there's lots of interesting options. I mean, you know, even in Norway at the moment, they're considering quite a few interesting alternatives. They have floating cable stayed suspension bridges, so that allow you to cross. So they have multi-span cable stayed bridges that are essentially floating with floating supports that can allow you to cross deep water. So there are all sorts of different options, but if it is possible to put in foundations at regular intervals, I think a medium span bridge together with long span navigation channels would be quite a typical approach to those long causeway type of structures. And there's lots of examples of them around the world. And I think even in Brunei, there's an example that wasn't built so long ago. Yeah.
Thank you very much, John. Thank you so much. Andrea, perhaps you would like to also to respond?
Yes, sure. Well, it is not easy to put together a feasibility studies in a couple of minutes.
Yeah.
And yes, as John mentioned, we are now for the longest span, slightly above 2,000 meters. We have the Akashi Kaiko is about 1,900. There is a one under construction in Turkey. Long span suspension is above 2,000. The longest is 3,300, which is just in the concept phase in Italy. So it was never started and potentially never will be started. Is a bridge with a long story. So of course we would think about solutions that will reduce the challenges, because of course the more you have a long span and the more you push your material, your design, and your technical knowledge, and also your construction methods to the limit. To go further into the investigation, of course, it's a matter of the requirements. Because first of all, we need to know the clearance, the width of the navigational channel, the site constraint, the water depth. And then I've been, for example, involved in some projects where it has, for example, decided not to utilize only bridges, but also to have part of bridge and part of tunnel, underwater tunnel. I always recommend to use bridges because they are nicer and more beautiful. But many times, it's a choice that the authority is called to do, because sometimes, of course, with tunnel you have the advantage that you don't see them. They're underwater, so you have a less impact. On the other side, a long span bridge is many times a prestigious project. If we think, for example, about the Millau Viaduct in France, it's a very famous bridge. It became famous with photos and videos going viral. You see this deck almost floating over the clouds. You will maybe not believe it. However, this bridge became a tourist attraction, and the area now is visited now, not now with COVID probably, but before COVID, it was visited by a large number of tourists. So just to summarize, it is not only a technical choice, but many times is also, a social impact and environmental impact. There are more and more requirements that you are called to put together.
Thank you very much, Andrea.
Pleasure.
Pak Ahmadi would like to respond on this.
Luar biasa ini pertanyaan sekali konsultan ini. Baik Pak, jadi memang tentang 7 kilo jembatan Batam Bintan ini memang kebetulan kita juga diskusi cukup dalam, di mana memang betul ini ada jembatan yang menghubungkan dua pulau, Batam dan Bintan. Di tengahnya ada pulau Tanjung Sau. Ya, ini terbagi dua section ya Pak ya, section 1 dan section 2, terutama yang ada di selat itu, jadi yang laut itu. Yang satu itu kira-kira mungkin 2,100 something lah panjangnya, antara Batam dan Tanjung Sau. Sedangkan Tanjung Sau menuju ke Bintan ya kira-kira sekitar 3.800-an something lah. Jadi 4 kilo, 2 kilo terus di tengahnya di Tanjung Sau, sisanya di perutnya di kanan kiri, Pak. Ya memang kalau bertanya, ini kan alternatif ya Pak. Ya mohon maaf kalau kurang-kurang pas, tapi kita juga sudah pernah berpikir tentang kira-kira model apa saja yang bisa kita kembangkan. Yang pertama memang di section 1 Pak. Di section 1 itu antara Batam ke Tanjung Sau sekitar 2 kilo itu ya memang kita kombinasi Pak. Jadi memang satu kita bisa menggunakan di tengahnya memang tetap cable stay Pak, yang seperti gambar di belakang kita itu, karena hanya itu yang bisa menjawab tantangan long span bridge yang bisa kita laksanakan di atas air laut yang sudah merupakan proven teknologi gitu. Jadi itu yang akan dipilih. Tentunya bagian yang lain adalah box girder Pak yang kita combine. Jadi itu sama Pak. Kalau kemudian yang di tengahnya juga yang satunya yang 3 kilo juga hampir sama. Di tengahnya yang bisa kita kembangkan kira-kira 500-an meter itu Pak. 500 atau 600 meter di tengah itu kita akan gunakan cable stay Pak kalau memang ini. Tentunya dengan model pilon yang A itu yang di tengah itu double pilon mungkin kita akan menggunakan seperti itu. Jadi memang ini tentunya masih ya Pak kasar ya. Tapi paling tidak itu bisa menjadikan pemikiran awal karena sebenarnya kita juga berdasar pengalaman kita mengajarkan di Balerang tidak jauh dari itu ya seperti itu Pak. Kira-kira kalau Bapak bertanya dan saya dijawab menjawab alternatif yang saya kembangkan seperti itu. Mungkin demikian Pak. Terima kasih.
Ya, terima kasih Pak. Sampai tadi ini pertanyaan Pak Prastiwo ya.
Ya,
mungkin ini sedikit aja juga. Dulu saya pernah di Batam kali 5 tahun, jadi ngerti-ngerti sedikit lah gitu. Jadi waktu awal-awal. Jadi yang perlu juga kita lihat itu adalah kedalamannya Pak, karena kedalamannya arusnya besar di situ. Tinggal nanti kita melihat apakah kita masih akan gunakan selat itu untuk lalu lintas kapal apa tidak. Kalau kita gunakan juga berarti clearance-nya harus cukup tinggi. Kalau tidak mungkin lain lagi. Itu jadi opsi-opsi itu yang nanti diinikan oleh bapak-bapak seperti Pak Ahmadi ini nih. Nah, tapi yang menarik tadi yang penjawab pertama, penjawab kedua juga unik juga itu jawabnya. Pertama yang dia bilang itu bahwa sejauh ini kan belum ada di dunia jembatan yang kabel stay yang free span-nya sampai lebih dari 3.500 meter, tidak ada. Kalau kita mau bikin sampai 4.000 meter itu, ya selain mungkin desainnya, tapi yang paling penting adalah construction-nya Pak. Construction-nya yang apalagi construction-nya itu yang mungkin kita belum tahu gitu ya. Tapi beliau menyatakan bahwa katanya nih di mana tadi di Norway katanya, mungkin dipikirkan dengan istilahnya floating suspension bridge multi-span. Jadi katanya tiangnya itu mungkin tidak sampai ke dalam, tidak sampai ke tanah keras, karena mungkin sangat dalam, maka lebih masuk akal kalau fondasinya itu di atas floating. Saya sendiri melihat, wah ini bagus sekali, wah luar biasa. Orang-orang teknis seperti Pak Ahmadi akan tertarik, kita akan banyak.
Seru Pak, kayak nonton.
Banyak, menarik lah kalau seperti gini. Itu satu. Yang kedua Pak Andrea, ini Pak Andrea bilang itu sejauh ini yang paling panjang katanya nih adalah di Selat Messina 2.300 dulu. Kalau kita mau bikin Selat Sunda itu kita juga studi itu ke Selat Messina. Tapi kan sampai sekarang dia ketawa Pak Andrea. Sampai sekarang juga belum terjadi itu di Messina Strait ya karena berbagai hal lah, mungkin terutama mungkin masalah ekonomi. Tapi waktu itu jadi proyek yang sangat menarik lah seluruh dunia karena waktu itu dipikirkan jembatan kabel stay terpanjang akan ada di Selat Messina. Mungkin udah 50 tahun kali desainnya. Nah, tapi beliau juga katakan jembatan itu kenapa menarik. Nah, tapi sebetulnya kalau kita mau agak kompromi dalam hal-hal tertentu mungkin kita bisa kasih alternatif, nggak harus jembatan, mungkin juga tunnel. Cuma tadi dia bilang kalau jembatan itu kan orang bisa sekaligus untuk turistik karena bentuknya elok dan lain-lain ya Pak ya. Ada perhitungan-perhitungan sosial yang lebih menang ketimbang tanah. Nah, ini semuanya kita serahkanlah kepada nanti para pemikir, para ahli, terutama Pak Ahmadi dan kawan-kawannya yang Bridge Engineer Indonesia yang akan membawa teknologi jembatan kita ke masa depan yang lebih modern begitu ya. Barangkali karena waktunya sudah mendekati jam 4, mungkin kita cukupi sampai di sini. So Mr. John Anderson, Mr. Andrea Mordini, Mr. Go Binli, dan Mr. Ahmadi Tricahyono, we approaching the limit of our time allocation. So we would like to thank you all very much for your contribution to share your knowledge with the Indonesian or your fellow Indonesian engineers. So with that, again, we would invite all of us to give a big applause to all the presenters. Big thank you for their contribution.
Thank you,
With
Pak.
that,
Thank you.
thank you, Pak. Thank you.
Thank you.
Thank you.
With that, I will hand it over back to the committee. Silakan Pak Habibie, terima kasih.
Ya, terima kasih banyak Pak Insinyur Wendy sudah dimoderasi selama kurang lebih 2 jam terakhir. Thank you very much. Before we close the session, Pak Bambang, you have something to say? Just like a closing statement.
Yes, okay, thanks, Pak. Yeah. First, I think I would only like to congratulate to all of you, yeah, all the participants, also moderator, and then the committee as well, and especially to Pak John Anderson, and then Pak Andrea Mordini, and Pak Kubin Lee, as well as Pak Ahmadi, yeah, for their presentation and then sharing experience, knowledge that will be very important to our engineers in Indonesia. Of course, the success cannot be measured right now or this afternoon, yeah, but depend on how our engineers can implement, yeah, what we have learned from all of you, and what can be extended from what we have from this discussion, yeah. And of course, Indonesia as a big country and a lot of islands, yeah, 17,000 islands, and we expect that someday we will be connected each other, yeah. And in this situation, I think the opportunity to build bridges, long span bridges, modern bridges, will be widely open. So welcome also to all of you to participate in the development of bridges in Indonesia, of course, yeah, and giving your knowledge, experience, and together with our engineers in Indonesia. Finally, I think we should be grateful, yeah, to all of you, to thanks, and hopefully you will be always in the good and the health and success in the future, even it's still in pandemic situation, yeah. Thank you very much. Good afternoon. I close this seminar officially. Thank you very much. Bye-bye.
Thank you.
Thank
Bye-bye,
you, Pak
Pak.
Bambang. So
Yeah.
can we all open the video so we can have photo sessions together? Pak Imam bisa di screenshot,
Mana nih?
Pak?
Oh, iya.
Pak Imam masih
Oke, Pak.
monitor? Ya, oke. So can we all open the video, please? Tadi saya lihat Pak Hermanto Dardak sempat bergabung.
Oh, ada
Oh ya.
Mungkin bisa dibuka videonya, Pak, foto bersama ya.
Oh, Profesor Anies juga ada. Thank you, Pak.
Sukses, Prof. Bambang.
Yeah.
Pak Irwanto, sukses.
Pak Mulia, kalau masih Ada di oke, ada.
Oke, 1,
Oke.
2, 3. Satu lagi. Oke.
Oke. Thank you.
Thank you very much.
Terima
Bye-bye.
kasih.
Bye.
Pak Fahmi,
Bye.
Pak Bambang.
Thank you,
Thank you, John. Thank you, Andrea.
Terima kasih.
Bye.
Ya.
Terima kasih sharingnya
Terima kasih.
semuanya.
Terima kasih, Pak. Ya,
Thank you
everybody.
very much
for all.
Ya, thank you very much.
Ya.
Thank you very much.
Pak Hermanto Dadak. Terima kasih, Pak.
Terima kasih, terima kasih.
Ya.
Pak Purnomo.
Ya.
Ya cuma suaranya doang, nggak ada orangnya. Orangnya pada kemana hilang?
Ya.
Sekali lagi saya ucapkan banyak terima
Yang
kasih.
kelihatan, yang kedengaran suaranya doang.
Ya. Kita tutup ya sesinya Pak ya.
Terima kasih.
Terima kasih semuanya. Sukses Pak Bambang.
Yo, terima kasih Pak.
Ya,
Anies.
sama.
Terima kasih.
Ya.
Terima kasih.
Pak Bambang. Ya.
Next, yo, terima kasih. Terima
Ya,
kasih.
sama.
Oh, Pak Anavia.
Ya Pak.
Pak Wendy.
Selamat sore Pak.
Ya, Pak Birazak. Ya.
Terima kasih Pak.
Thanks everybody. Mas Pur, terima kasih.
Betul, Mas Pur. Pak Coki.
Thank you,
Pak.
Everybody.
Ya, ucapkan permohonan maaf. Jika selama acara berlangsung terdapat
Oke,
kesalahan yang
terima kasih. Selamat sore.
semoga dengan dilakukannya kegiatan pada hari ini akan mendapatkan banyak manfaat dan banyak ilmu yang didapatkan.